Welcome to Lecture 11. In this lecture, we will study some of the regularization techniques that allows us to minimize the effect of overfitting problem in machine learning. In the previous class, we discussed the details of the overfitting problem, and we listed 4 common reasons. For instance, using excessively powerful hypotheses to solve a simple problem, or high stochastic noise, deterministic noise presence, as well as if data is limited, these all can be considered as the cause of overfitting. Today's lecture will focus on techniques that will help us to address the overfitting problem via regularized hypothesis set. In particular, we will discuss a technique called weight decay based regularization, and we will briefly study the regularization and its connection to VC theory. And we will conclude today's lecture by discussing general regularizers available or widely used in machine learning tasks. Let's revisit the following regression example. Here we are given 5 points along with the target function in blue. Okay? The target function, we said, is a second order polynomial generating these points. And these points are actually a bit noisy. Okay? They have stochastic noise in it. Now the task is to fit a hypothesis on this point and assess its performance. For example, let's assume that we use 10th order polynomial and that our fit results as follows. Okay, this red line. We notice the fit is perfect. In other words, in sample error is 0. However, as discussed in the previous class, we can expect large out of sample error because we are using a hypothesis of higher complexity than the original target function that generates the data. And we can say that our hypothesis overfits. We mentioned 4 general cases of overfitting. When using excessively powerful hypothesis again, well, this is a case, or when you have high stochastic and deterministic noise. Okay, and the last cause or possible cause of overfitting is when the amount of data is limited. These all can be considered to cause overfitting. In this example, we can assume that there are 2 causes. First, the presence of stochastic noise in the data, okay? And then we're using more powerful hypothesis than needed. The target function in blue is second order, but we are using 10th order polynomial to fit the state. Okay, 10th order overfits. So today we'll see how we can control the complexity of hypothesis from overfitting to regularized fit. This graph shows here the good fit. Even though visually we can see that the red lines doesn't perfectly pass through all the points, the out of sample error for this kind of regularized fit is expected to be good. Let us try to address this problem from the perspective of controlling the complexity of hypotheses we used to minimize our fitting problem. Let's assume that our hypothesis consists of nested structure, all the hypotheses that we consider, which includes all possible polynomials of varying degree, including tens, second, or even higher order polynomials. Since we know that these data were generated by second order polynomials, one idea would be to step back from using 10th order polynomial to second order polynomial. Similar problems are studied deeply in functional approximation, functional analysis field, under the historical name for solving ill-posed problems. In machine learning, however, we are more interested in heuristic approach of answering the question of how can we step back from more complex model or hypothesis to a simpler one. Let's imagine that our hypothesis set consists of polynomials of order q. This is a nonlinear transformation function. You can think of it as a function that takes your input, which is a scalar, and maps it into 2 different feature space, which is constructed based on different combination of the input scalar, 1, x squared up to x to the q. Okay, once we transform our input, we can perform a linear regression and obtain the weights, denote w tilde by w. So if our polynomial is order of 10, we will have the following hypothesis, right, with the corresponding weights. So hypothesis H10 will have 11 weights, W0 up to W10. And these are scalar values of our input feature mapped into different space of Z. And here, second hypothesis, which is the second order polynomial transformation. And we have here three weights, W0, W1, W2. So we can think of this H10 as a 10th order polynomial fitting, H2 as second order polynomial fitting. It's also easy to see that 10th order polynomial has more weight parameters and thus is more flexible and powerful than H2. However, from our previous example, H10 is prone to overfitting due to the complexity of the model. This can be also explained in terms of VC dimension, that 10th order polynomial is more powerful and has higher VC dimension. Now, if we return to the same question that we asked before, how can we step back from using 10th order polynomial into second order polynomial? Then one straightforward answer would be applying constraint, simply setting the weights to 0, whatever above W2. So W3, 4 up to 10 would be equal to 0. And this is a constraint. We are telling that given 10th order polynomial, we're imposing that all the weights above W2 should be 0. Okay, this constraint can be understood as a restriction that allows us to step back to using second order polynomial. Now we have a condition or a constraint that imposes on stepping back from using 10th order polynomial into second order polynomial. If we compare 10th order without constraint and 10th order with constraint subject to following constraint, we can think or assume that this is constraint form of the 10th order is equivalent to using second order polynomial. Because most of the weights are forced to be 0. And we won't be able to learn or change those weights to minimize the error function of our interest in sample error function. We can classify these kind of problems as constraint optimization problem of in-sample. So we want to find the weight or the hypothesis that will minimize our in-sample error function. Okay, this can be mean squared error function, or cross-entropy error function, in-sample error function, or 0-1 error function, subject to the following constraint. Even though we have 11 weights that can be tuned, which is 10 plus 1, we are imposing minimize in-sample error subject to that most of the weights are 0, starting from W3, 4, and 10. While in this case, we don't have any constraint, so SD stands for subject to. You may wonder why to do this? Why can't we just use second order polynomial? What's the point of introducing these constraints and making the problem more difficult to solve? It makes sense to just use second order polynomial, as most weights are forced to be 0. Okay, also can be considered as a hard constraint. And with a constraint, the final 10th order polynomial model can be equivalent to using H2. Nonetheless, the answer will be different if we loosen the constraint, if we don't impose most of the weights to be 0. Here, we can change from hard constraint 10th order polynomial to a looser version of 10th order polynomial, where we don't force the weights above W2 to be all 0, but soften E to allow any 3 weights out of all 11 weights in H2. Okay, this one is softer version or looser version, not soft. This one is hard constraint. All the weights above W2 should be 0. As a result, we can obtain H2 and then perform regression by minimizing in-sample error weights W0, 1, and 2. While here, this is a little bit looser version because we're not asking all of these specific weights to be 0, but saying that only 3 of the weights are allowed to be non-zero, or any 8 weights out of 11 should be 0. Then we perform regression, let's call it as H2 prime, minimizing sample error, subject to the following constraint. This constraint, again, says take any weight combination, W10, W5, W0, or any other possible combinations, and minimize your in-sample error. This results in a hypothesis which is more flexible than H2, or more flexible because using W or W10 is more useful or can be more useful than using just W2. And also we can say that it is less risky than tensor the polynomial. Risky to overfit because we are still controlling the complexity, whereas we still have some constraint. However, we should note that this optimization leads to seek a combinatorial quantity. And finding the best weight combination out of all possible combinations is a relatively hard problem to solve. And one way to resolve this issue is to consider a similar but alternative optimization problem, which further softens the constraints. For instance, we would like more of a softer constraint as follows. Given a budget C for total magnitude squared of the weights, instead of the harder constraint that we considered above, where we had to set some of the weights to 0 simply, we just want them generally to be a small value. This can be thought of an soft order constraint. Okay? Instead of asking 8 out of 11 weights to be 0, we can have some different form of it. Instead of asking all of them as 0, we can ask them to be small value. Or if we put it another way, instead of asking to find 3 best combinations of the weight that minimize in sample error in a sparse vector, we can think of asking or controlling the length of the norm of the weight vector from taking large values by imposing the following C, the upper bound. In other words, we don't want the weight vector to grow and take all possible values, okay, in order to minimize the error function, but restrict its length or growth by a budget C. For example, if you want to consider tens order polynomial with norm equal to 1, the length of the weight vector, we could set C equal to 1, and most of the weights can be expected to be a small value or even 0. This restriction could potentially result in a very small and a tiny weight values, but not 0. So we can think of it as a softer constraint on the weights. Now, the optimization problem we're trying to solve is as follows, which is easier to solve than this version of it, loose version of it, where we asked most of the weights to be 0. The types of the hypothesis h of C is our constraint, another constraint on the weights, overlaps with the h2 prime. However, it's not exactly the same. And we know that this version of the constraint optimization is soft and smooth structure over the values of C. For example, we can have h of 0, okay, if this is 0, though we are imposing all weights to be 0. And we can also have values like 1.126 or even higher up to infinity. Okay, and using all possible nested structure of our hypothesis and using constraint, we can try to find equivalent tensor polynomial. Right? So now regularized, we call them as regularized hypotheses and denote by WREG. Okay, and we consider them as an optimal solution to this problem, which signifies the regularization, okay, as opposed to W-lean, which was the original solution to unconstrained linear regression problem. Now our task is to solve this optimization problem. Let's take a look at this quiz. So for Q greater or equal to 1, okay, Q is order of the polynomial, which of the following hypotheses, the weight vector of the following dimensionality, Q plus 1, is not in the regularized hypothesis set, H of 1? Is it the first one, second, third, or fourth? Think about it and send your answers to me. You'll get a bonus point. Let us revisit the linear regression problem again, where we were interested in minimizing the mean squared error function as shown here. Okay, this is an in-sample error function that we use for linear regression. We can form the regularized form of this in-sample error minimization with the following constraint, which means that the norm of the weight vector that minimizes our in-sample error should be upper bounded by C. Okay, here the Z, this is a matrix form of this in-sample error. Okay, if you remember from the previous classes. Here D represents our input data. It's just a different name for X. In this case, we mean that our X has been mapped into Z space that has been transformed by a nonlinear polynomial function. However, you can think of it as a regular X. Okay, the matrix form of in-sample error can be written as follows, as we did in our linear regression. The Q, the dimensionality of our weight vector, coincides with the order of the polynomial transform, plus 1. And the solution of the problem is now restricted by a hypersphere, square root of C. Okay, this is a feasible region with the following hypersphere of radius square root of C. How can we solve this problem? It's a constraint optimization problem now. In unconstrained linear regression problem, we found the solution of the minimum by matrix inversion. We had the analytical solution. However, now we have a constraint to consider. Of such constraint optimization problem can often be found by using the Lagrangian method. We can define Lagrangian function first, which will be the sum of the original objective function plus a term that involves the constraint, the functional constraint, and also a Lagrange multiplier. But first, let's try to get the geometric interpretation of this constraint optimization problem. We can visualize, first of all, the solution by an ellipsoid or contour map, which is shown in the blue. The solution will be located at this point. And here, the boundary of the ellipsoid consists of the same value for E in. And any value inside the boundary is smaller in-sample error value. Any value outside will be equal to higher or larger in-sample value, error value. Now we can also take a look at the contour map of our constraint. So W transpose W. And here, this line, the red line, corresponds to the value of C. So the constraint means that we have to be inside this red ellipsoid. Solution given by linear regression alone, which is W lin, is at the centroid of this blue ellipsoid, okay, since it minimizes in-sample error. Because we want to choose a point within this given constraint, red ellipsoid, which minimizes our in-sample error, it is reasonable to think that we have to go as far as out as we can within the red ellipsoid. Therefore, the constraint we will actually be using is this one, right? W transpose W is equal to C. Since the best value of in-sample will occur at the boundary of red ellipsoid. Of course, if the red ellipsoid was large enough to contain W lin, the solution of the original in-sample error, if the radius was big enough, then the solution would be W lin, okay, which is the minimum of in-sample. However, in this case, okay, we need to find a point either here or here or here. The minimization of only, let's say, unconstrained linear regression involved computing the gradient of in-sample error and moving in the negative direction, right? In the decreasing direction of, that will give us a decreasing direction of the in-sample error. And based on this contour map, the gradient, negative gradient, will always be orthogonal to this blue line. And then the normal vector of our constraint, okay, will be also orthogonal to the surface of the red ellipsoid or contour map. So if the gradient and then the weight of the constraint or normal of the constraint is not parallel, we can decrease in sample error without violating the constraint if they're not parallel. So let's call now the optimal solution by a WREC. Okay, WREC is a weight vector that satisfies both the constraint and achieves the minimum of in-sample error under this constraint. At the optimum, okay, the WREC, the weight, and then the gradient of the in-sample error will be parallel or collinear. They will be proportional. So the gradient of the in-sample will be here at this location, and then the weight vector, which WREC will be pointing towards this at this intersection. So we can tell them as negative gradient of in-sample is proportional to the optimal WREC, right? And then we can form a Lagrange function based on this relationship. So now the gradient minus WREC with some normalizers added to lambda is parameter to its constant over n is equal to 0. Okay, now the task is to find this lambda, which we call as a Lagrange multiplier, that will minimize these two terms. So how can we solve this problem? Right, we want to make sure that the gradient of in-sample error plus the term WREC should be equal to 0. Okay, this is a new form of the optimization problem. And lambda, let's call it as Lagrange multipliers. The gradient of our linear regression in sample error, which was mean squared error, is equal to the following. Right? We have derived this earlier. 2 over n, z transpose z, this is our data, WREC minus z transpose y. And when we solved linear regression without this constraint optimization, WREC could be obtained by inverting these matrices, right? Matrices. However, in our case, we have also another term called WREC, which comes from the constraint, okay, of the optimization problem. Now, the 2 over n, which we added, was intentionally added to eliminate together, okay? Eliminate this 2 over n that we would have obtained from gradient of in-sample error or mean squared error. So the solution of this, if you solve for WREC, will be equal to the following. It's easy. You just have to rearrange, collect the terms WREC, okay? Take this to the other side of equality and invert this term. So z transpose z plus, we are left with lambda inverted, and z transpose y. Okay, this will be the solution. Optimal solution at the optimal solution for our regularized linear regression problem. And this solution is called, or this problem is called as rich regression problem. It's that in statistics field. Okay. Now let's give an equivalent name to this. So we can call this as augmented error minimization. So for example, this is a gradient of our in-sample error plus our regularizer term, right? This is quadratic term. So augmented error now consists of in-sample plus one term. And we call it as modified augmented error function. Now, okay, we're dealing with regularization with augmented error instead of constraint in-sample error minimization. Then the solution would be W that will minimize our augmented error for some non-negative lambda. Okay, so we can show in practice that minimizing unconstrained augmented error function effectively minimize C-constrained error in sample error function. And we can show their relevance. For example, the value of C and lambda of augmented error are related. Now, first, let's take a look at how minimizing augmented error helps overfitting problem. Okay, so when we minimized the original in sample without regularizer, where lambda is equal to 0 in our augmented error, then we will see the following effect. This is overfitting case. And by just adding small regularizer value with some lambda small number, we can see its results. Okay, so we are controlling the weights, taking any possible value. We are restricting the weights. And as a result, the red hypothesis almost perfectly fits the data. Although as we increase the lambda, we see we're imposing more restriction. Okay, we're controlling the complexity, flexibility of our hypothesis. If lambda is 1, we are almost approaching the linear hypothesis. Okay, so from tensor order polynomial, with some small regularizer, we can restrict it to second order polynomial, or even first order or linear function. And this is all thanks to minimizing this regularized form of augmented error. So now let's come back to the relations between lambda and then C. So lambda appears in the augmented error. C is in-sample error with C constraint, right? So upper bound. So that if C is big, it already contains W lean. Okay, so lambda and C is inversely proportional. So if lambda is 0, then we are minimizing original in-sample error. If lambda is big value, then C will be small, and the minimizing two terms will be important. So more focus will be given to minimizing the second term of our augmented error. Right. So here in this example, we have seen in-sample error to be mean squared error. However, the following regularization applies to any kind of most available in-sample error functions. Now let's take a look at the regularization and then VC theory and their possible connections. We said that regularization by constraint minimizing the original in-sample error subject to some constraint is equivalent to minimizing augmented error. Okay, augmented error, which contains two terms, in-sample error plus a regularizer, right? So minimizing augmented error is more friendlier than minimizing the original constraint optimization in sample plus this inequality. And they're both related by C and lambda parameters. Now, if we think about VC bound or VC guarantee on minimizing sample error, we had the following. Out of sample error was upper bounded by in sample error plus some complexity term of our hypothesis. Do you see the similarity? So augmented error, okay, and in sample error plus some complexity term. So augmented error and VC bound, we can explain that fast. So regularized minimization of augmented error controls the complexity of single hypothesis, right? This penalty parameter. While in VC bound, this omega of H is a generalization price or complexity of the entire hypothesis set, defined by VC dimension. So if the omega of our weight represents omega of the complexity of hypothesis, well, then minimizing augmented error would be the better proxy of out of sample error than in sample error. Okay, so minimizing augmented error is better than minimizing the in sample error, okay, non-regularized one. So it is a better proxy heuristically. And then augmented error enjoys the flexibility of entire hypothesis set. Now let's take a look at different version of regularizer omega of W. Okay, here remember we want the constraint that moves in the direction of target function. And depending on omega, the solution to augmented error minimization can be different. And the property of omega also is important. So for instance, we can have a target dependent regularizer with some properties that contains some properties of target if known. For example, symmetry regularizer will be the following. Okay, we are only considering the odd cues or plausible directions towards smoother or simpler or stochastic deterministic noise, both non-smooth. Then we may consider using L1 regularizer, which is the L1 norm on the weights. So symmetric regularizer, L1 norm regularizer, or L2 norm regularizer. So among others, L2 norm regularizer is easier to optimize because of its quadratic nature and is widely used. So L2 norm, L1 norm regularizer are widely used. So one can come up with different regularizer depending on the application. Here we just very briefly discuss symmetry property, sparsity, or weight decay property. So regularizer should be designed based on some properties of our target function that brings us closer to the target function, while error function or error measure is usually user dependent. We can visualize the contour map of L2 norm regularizer and L1 norm regularizer. Okay, this is the ellipsoid of in-sample error regularizer, in-sample error regularizer. So we can see that L1 norm imposes sparsity in solution. However, it's not differentiable, non-convex everywhere. Well, L2 norm, okay, which is defined by the following, is convex, differentiable, and easy to optimize, and will impose smooth solution. So depending on the application, you can choose L2 or L1 norm, okay? So if you want sparse solution, in other words, if you want most of the weights to be zero at the solution, you can use L1 norm based regularization, this form. Okay, this will make most of the weights to be zero. And L1 norm also used in most applications that may involve in feature selection or feature extraction. Now let's take a look at the role of lambda in our regularizer, given stochastic and deterministic noise. All right, so proper choice of lambda is very important. Proper choice of lambda. For example, if you have more stochastic noise, then we need more regularized or regularization. For instance, if we denote the variance of stochastic noise by sigma 0, 0.25, 0.5, right? When we have non-noisy, no zero stochastic noise data, then the regularization parameter will be equal to 0. So we don't need to penalize or apply regularization. If you have noise, more stochastic noise in our data, we may apply some values around 0.6 or 7, okay, and achieve small out of sample error on the generated test data. And if you have more noise in data, then more stronger lambda, okay, so forth. It is similar case in the case of deterministic noise. So if you have, so we said deterministic noise is about complexity of our hypothesis. So hundredth order polynomial, 30s, 15s. Okay, if you're using hundredth order, right, you may want to use more stronger regularization, 30s or, okay, 15s, 0, depends. So basically, if you have more noise in your data, more regularization needed. It's similar to more bumpy road, putting brakes more frequently. Okay, so the choice or the strategy for selecting the lambda will be discussed in the validation lecture, which will be the subject of our next class. So that's it for today. Let me summarize briefly. So regularization is a cure for overfitting. We started with regularization, the regularized hypothesis set today, where our original hypothesis had some constraint. Okay, based on that, we introduced more looser constraint, more softer constraint, and came up with a augmented error, which had two terms, in-sample error plus some regularizer. And then we briefly talked about regularization and VC theory, that they are connected. And regularizers can be target dependent plausible and friendly, right? So we've reviewed three commonly used regularizers: symmetry, L1 norm, which induce sparsity, and L2 norm regularizers. And there are many more. So you can combine L1 norm and L2 norm in regularizing your hypothesis. So that's it for today. In our next class, we will see how we can choose those parameters or hyperparameters such as lambda. See you.